What if I told you that everything you see, everything you've ever touched or felt, makes up less than 5% of the entire universe? That's not science fiction. That's a fact that keeps the world's sharpest scientific minds up at night. For all our incredible progress, for all the stunning images from deep space, and the power we've unlocked from the atom, we are totally adrift in a cosmic ocean of ignorance. We think we get the rules, but the universe keeps showing us we've barely read the first page. The most fundamental things about our reality, the stuff that holds galaxies together, the force that's pushing the universe apart, the very nature of existence itself are still profound mysteries. Today, we're pulling back the curtain on what we think we know to stare into the abyss of the unknown. These are the 5 biggest physics mysteries we still can't solve. For centuries, physics has been a story of bringing things together. Newton figured out that the force pulling an apple to the ground is the same one holding the moon in orbit. Maxwell connected electricity and magnetism into one beautiful theory. Einstein wove space and time into a single fabric. Each step brought us closer to a complete picture of reality. But today, that picture is full of holes. The more we learn, the more we realize just how much we don't know. Our most successful theories, the standard model of particle physics and general relativity, are like 2 brilliant, stubborn geniuses who refuse to talk to each other. They work perfectly in their own realms, the incredibly small and the unimaginably large, but they completely break down at the extremes. And where they break, deep paradoxes pop up. The puzzles we're about to explore aren't just small gaps in our knowledge. They are fundamental cracks in the very foundation of physics. Solving just one of them wouldn't just win a Nobel Prize. It would rewrite our understanding of everything. So, let's start our journey to the edge of what we know. The cosmic ghosts. What is dark matter? Our first mystery kicks off with a simple observation that led to a universe-shattering conclusion. When astronomers looked at galaxies, they knew something was off. The stars at the outer edges of spiral galaxies were moving way too fast. A lot more. An invisible, unseen mass. A kind of cosmic ghost whose gravity was the only thing keeping galaxies from flying apart. They called it dark matter. Based on everything we know about gravity, these speedy stars should have been flung off into deep space. Like a kid flying off a merry-go-round that's spinning too quickly. The gravitational pull from all the visible stuff in the galaxy, all the stars, gas and dust, wasn't nearly strong enough to keep them in orbit. The only logical, though totally baffling, conclusion was that there had to be more stuff out there, and this isn't some small rounding error. Scientists estimate that dark matter makes up about 27% of the universe. For comparison, all the ordinary matter that we can see and interact with every single star, planet, and galaxy is less than 5%. Maybe dark matter is made of different particles, like incredibly light or maybe it's something even wilder, like primordial black holes created moments after the Big Bang. Some have even dared to ask the ultimate heretical question: what if there is no dark matter? What if our theory of gravity is wrong? These modified gravity theories suggest that across vast cosmic distances, gravity just doesn't work the way Einstein predicted. But so far, these alternative ideas have had a hard time explaining all our observations as neatly as the dark matter theory does. We are the odd ones out. The universe is dominated by a substance we can't see, touch, or detect directly. We only know it's there because of how it gravitationally pulls on the things we can see. The vast majority of the universe's mass is a complete unknown. A silent, invisible scaffold that the visible universe is built on. Until we figure out what it is, we can't really say we understand the galaxy we live in, let alone the universe. So, what is it? That's the multi-billion-dollar question. For decades, the leading idea has been that dark matter is made of undiscovered subatomic particles. In a moment of charming simplicity, physicists called them WIMPs, which stands for weakly interacting massive particles. Experiments like the Lux Zeppelin or LZ detector, located nearly a mile underground in South Dakota, use giant tanks of supercooled liquid xenon, hoping for the tiniest chance that a WIMP will hit a xenon nucleus and create a small flash of light. As of recent analyses in 2024, after sifting through mountains of data, these experiments have found absolutely nothing. No definite sign of a WIMP has ever been picked up. These hypothetical particles would be weakly interacting, meaning they barely ever bump into normal matter, which explains why they're so hard to find. And they'd be massive, which explains the huge gravitational effects we see. To find these WIMPs, Scientists have built some of the most sensitive detectors ever imagined, placing them deep underground to shield them from cosmic rays and other noise. The continued silence from these experiments has pushed scientists to think about other ideas. The mystery of dark matter is a huge reminder of our place in the cosmos. The runaway universe. What is dark energy? If dark matter was a surprising twist, our next mystery is the shocking season finale that changes everything. For most of the 20th century, the biggest question in cosmology was, how will the universe end? The general thinking was that it would go one of two ways. They were studying distant supernova exploding stars to measure how the universe's expansion rate has changed over time. They fully expected to see the expansion slowing down. What they found was the exact opposite. The expansion of the universe isn't slowing down at all, it's speeding up. Either the universe had enough stuff, and therefore enough gravity to stop its own expansion and collapse back in on itself in a big crunch, or it didn't, and it would expand forever, just at a slower and slower pace, fading into a cold, dark, big freeze. In the late 1990s, two separate teams of astronomers tried to settle it once and for all. Is dark energy a new kind of energy field? Maybe a fifth fundamental force of nature? Or could general relativity itself be breaking down on the scale of the whole universe? Will the acceleration continue, leading to a big rip, where galaxies, stars, and even atoms get torn apart? Or will it change course? We have no idea, because we don't know what it is. We only know that 95% of our universe is made of dark matter, and dark energy do things we can't see and do and understand. In 2024, results from major projects like the Dark Energy Spectroscopic Instrument hinted that dark energy might not be constant. The data suggests that its influence might be evolving and weakening over time. If that's confirmed, it would rule out Einstein's cosmological constant and trigger a revolution in cosmology. There are even some wild theories, like one from researchers in New Zealand in 2024 suggesting dark energy doesn't exist at all, and the acceleration is just an illusion, caused by our place in a lumpy universe where time flows differently depending on where you are. And dark matter is about 27%. Dark energy is thought to make up a mind-boggling 68% of the universe. That means the vast majority of our cosmos is made of an unknown energy that's actively shoving everything apart. This discovery completely rocked the world of cosmology. It was like throwing a ball in the air and watching it accelerate into space instead of falling back to Earth. To explain this cosmic acceleration, there had to be some kind of force pushing everything apart, a sort of anti-gravity that takes over across immense distances. Physicists gave this mysterious force a name as strange as its nature: dark energy. In this view, every bit of empty space has its own built-in energy. As space expands, more space is created, and with it, more of this energy, which then pushes the expansion to go even faster. The problem is, when physicists try to calculate how much energy the vacuum of space should have based on quantum theory, the number they get is catastrophically wrong. It is about 120 orders of magnitude, that is, a 1 with 120 zeros after a bit bigger than what we actually observe. This has been called the worst theoretical prediction in the history of physics, and here's where the numbers get even crazier. While normal matter is about 5% of the universe, so what could it be? The leading theory is that it's a property of space itself, what Einstein once called the cosmological constant. This massive gap between theory and observation tells us we're missing something huge. The mystery of dark energy holds the key to the ultimate fate of everything. The observer effect, the quantum measurement problem, our first two mysteries took us to the far reaches of the cosmos. For our third, we have to go in the opposite direction, to the bizarre realm of the impossibly small, the world of quantum mechanics. Down here, the rules of our everyday world just don't apply, replaced by a reality of probabilities and At the heart of it all is one of the most confusing puzzles in science. The measurement problem. The superposition just vanishes. The wave function collapses, and the particle instantly snaps to a single, definite location. This process is random and irreversible. The smooth, predictable math is violently interrupted simply by being observed. Here's the deal. Quantum mechanics tells us that before we measure a particle, like an electron, it doesn't have definite properties. It's not in one specific place or moving at one specific speed. Instead, it exists in a fuzzy cloud of all possible outcomes at once, a state we call a super. The particle is, in a very real way, in many places, at the same time. The many worlds interpretation, for example, says the wave function never collapses at all. Instead, Every time a measurement happens, the entire universe splits into multiple copies. In one universe, the electron is here. In another, it's over there. Every possible outcome happens, just in its own parallel universe. It's a neat solution to the collapse problem, but it comes at the cost of creating an infinite number of unobservable universes, which a lot of scientists aren't ready to buy. This is described by a mathematical tool called the wave function, which evolves smoothly and predictably. And then you have ideas like the relational interpretation, which argues that an object's properties only exist in relation to something else, meaning there's no single, objective reality to begin with. But the moment you look at the particle, the second you try to measure where it is, something weird happens. Is the universe a single timeline, or a branching tree of endless possibilities? Is there an objective world out there that exists without us? Or is reality itself created, in some way, by the act of looking at it? A century after it was first posed, we're still not much closer to an answer. This is the measurement problem. What exactly is a measurement? Why does the simple act of looking at a quantum system force it to drop its ghostly superposition and pick a single, real state? And what counts as an observer? Does it have to be a person, a camera, a rock? The theory gives us no clear answers. For almost 100 years, physicists and philosophers have been tearing their hair out over this, and the fact that there's no consensus is kind of an embarrassment. As of today, there are more than a dozen different interpretations of quantum mechanics, and not a single one has been proven correct. The oldest and most famous is the Copenhagen interpretation, which basically says, shut up and calculate. It says the collapse is real but doesn't explain why, treating it as a basic rule of nature. It works for doing the math, but it's deeply unsatisfying. Frustrated by this, other physicists have suggested more radical ideas. Other ideas, like objective collapse theories, suggest the collapse is a real, physical process that happens on its own, may be triggered by gravity, without needing an observer at all. The measurement problem isn't just a philosophical hang-up. It gets to the very core of what reality is. The beginning and the end. The origin and fate of the universe. For as long as we've been human, we've looked at the stars and asked the biggest questions. Where did all this come from? And where is it all going? In the 20th century, we found what seemed like a solid answer: the Big Bang. The theory says the universe began about 13.8 billion years ago from an unbelievably hot, dense point and has been expanding and cooling ever since. This idea is backed by a mountain of evidence, from the stretching of light from distant galaxies to the faint afterglow of the Big Bang itself, the cosmic microwave background, and it has sent back some stunning and confusing results. Throughout 2024, JWST has shown us galaxies in the early universe that are way brighter, more massive, and more complex than our models said they should be. It has found supermassive black holes that seem to have gotten way too big, way too fast, while some of these impossibly large galaxies have now been explained by the extra light from ravenous black holes at their centers. If dark energy gets stronger, it could lead to a big rip, where the expansion becomes so violent it overcomes gravity itself, tearing apart galaxies, solar systems, planets, and finally, the very atoms we're made of. If dark energy reverses course, it could bring back the old fear of a big crunch, where the universe collapses back in on itself, maybe even triggering a new Big Bang in an endless cycle. The telescope is consistently showing us that the early universe was a much busier and more developed place than we ever imagined. These discoveries aren't breaking cosmology, but they are forcing scientists to seriously rethink how the first stars and galaxies came to be. Many theories, including some versions of string theory and cosmic inflation, predict a multiverse, a vast collection of parallel universes, each one potentially with its own laws of physics. Is our universe just one bubble in an infinite cosmic foam? It's an incredible idea, but one we have absolutely no evidence for right now. The story of the universe's origin and fate is the grandest tale of all, but its first and final pages are still blank. But as good as it is, the Big Bang Theory doesn't actually describe the beginning. It describes what happened in the moments after the beginning. It tells us nothing about that initial instant, the so-called singularity where our laws of physics just give up. What set off the Big Bang? And what, if anything, came before it? Science currently has no answer. It's the point where our knowledge just stops. The James Webb Space Telescope was supposed to help us get closer to that beginning than ever before. These questions about our origin are matched by equally deep questions about our ultimate fate. As we saw with dark energy, the destiny of the universe is tied to that mysterious force. If dark energy stays constant, the universe will probably keep expanding faster and faster, leading to a big freeze, or heat death. In that scenario, galaxies will fly so far apart, they'll disappear from each other's view. The stars will burn out, and the universe will become a cold, dark, and empty place. But if dark energy changes over time, as some 2024 data hints it might, other, more dramatic endings are on the table. And then there's the most mind-bending possibility of all, that our universe isn't the only one. The cosmic coincidence. Why is the universe just right for life? Our final mystery is maybe the most philosophical of them all. It's not about some unknown substance or a weird observation. It's about the laws of physics themselves. When you look at the fundamental numbers that run our universe, things like the strength of gravity, the mass of an electron, the speed of light, you find something incredible. Take the strong nuclear force, the glue that holds atomic nuclei together. If it were just a few percent weaker, protons wouldn't stick together, and the only element would be hydrogen. No stars, no planets, no us. If it were a tiny bit stronger, all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for long-lived stars like our sun. They seem to be perfectly, exquisitely fine-tuned for life to exist. The numbers are what they are, and we're here to wonder about it because, obviously, we couldn't exist in a universe where they were different. This is a version of the anthropic principle, it's true, but a lot of people find it unsatisfying in this view. The fine-tuning is just an illusion. We just don't get the underlying physics yet. The trouble is, we have no idea what that theory looks like. If our universe is just one of countless others, and each of those universes has a random set of physical constants, then it's not surprising at all that we find ourselves in one that can support us. We just won the cosmic lottery. The multiverse gives a scientific-sounding explanation for fine-tuning without needing a creator. The huge catch, though, is that for now, at least these other universes are completely unobservable and untestable, which makes some critics argue it's not really science, but metaphysics, because it doesn't really explain why the numbers are what they are. We know its value is incredibly small, but if it had been even slightly larger, its repulsive force would have blown the early universe apart. Before any stars or galaxies could even begin to form, it forces us to ask whether our universe is a unique creation, a fluke, or just one of an infinite number of possibilities. It's a mystery that makes us think not just about the cosmos, but about our own significance within it. The odds of this constant being life-permitting just by chance have been compared to throwing a dart across the entire universe and hitting a bullseye 1 millimeter wide. This is the fine-tuning problem. Why do the basic rules of our universe have these specific life-permitting values? Is it an impossibly lucky coincidence? Or is it a sign of something more? If you tweaked these values, even by a microscopic amount, the universe as we know it would be impossible. Or look at the value associated with dark energy, the cosmological constant. It's not just one or two numbers, it's a whole list of them, all balanced on a razor's edge. There are three main ways to think about this. The first is that we just got lucky. The second option is that there's a deeper yet to be discovered theory of everything, that will one day show that these numbers have to be the values they are for mathematical reasons. The third, and maybe most popular idea among cosmologists, is the multiverse. The fine-tuning problem pushes physics right to the edge of philosophy. So there you have it. The cosmic ghost holding galaxies together, the anti-gravity tearing space apart, the paradox at the heart of reality, the mystery of our beginning and end, and the incredible coincidence that lets us exist at all. Dark matter, dark energy, the measurement problem, the universe's origin and fate, they all tell us that our current understanding of physics, for all its successes, is incomplete. They are whispers from the universe telling us there is a deeper reality, a more fundamental set of rules that we haven't even begun to grasp. They show us the very limits of our knowledge, the line where science meets up. What connects all these massive puzzles? They're all signposts pointing to the same place. Every one of these mysteries is a frontier, an invitation to the next generation of thinkers, dreamers, and explorers. A little over a century ago, many thought physics was basically finished, right before relativity and quantum mechanics blew everything wide open. Today, with 95% of the universe still a complete mystery, we might be on the verge of an even bigger revolution. The story of physics is nowhere near its end. In fact, it might just be getting started. The universe isn't a closed book. It's an endless library of mysteries just waiting for us to read them, and the quest for answers is the greatest adventure there is. But these aren't reasons to give up. There are reasons to get excited. What do you think is the biggest mystery in physics? Is there one that keeps you up at night? Let me know your thoughts in the comments below. And if you enjoyed this trip to the edge of human knowledge, make sure to hit that like button, subscribe, and ring the notification bell so you don't miss our next dive into the great unknowns of science. Thanks for watching.